Your lecturer is Lawrence Weinstein. Dr. Weinstein is a professor of physics at Old Dominion University and a researcher at the Thomas Jefferson National Accelerator Facility. He received his doctorate in physics from the Massachusetts Institute of Technology. Professor Weinstein is the author of Guesstimation with John Adam and Guesstimation 2.0 about techniques for approximate solutions to any problem. Frequently honored for teaching and research, he is the recipient of the Virginia Outstanding Faculty Award and a Fellow of the American Physical Society.
Did you know our galaxy has objects called neutron stars that are just giant nuclei? And did you know that the amount of uranium fuel needed to run a large nuclear power plant for an entire year is so small that it could fit under your kitchen table? And did you know that doctors increasingly rely on nuclear medicine techniques, which go by friendly sounding names such as PET scans or CAT scans or proton therapy? What is nuclear physics and where did it come from? During the 20th century, nuclear physics emerged from the shadow of chemistry to become much more than chemistry. For example, the sun is not a chemical fire. Lord Kelvin in the 19th century did not know about nuclear physics. This led him to wildly underestimate the age of the sun and of the Earth. Lord Kelvin was wrong because, to everyone's surprise, the dream of medieval alchemists has been attained. One element can change into another. The sun changes hydrogen into helium. But it can't be done with chemistry. The philosopher's stone of the alchemists turns out to be the nucleus, involving forces much greater than anything in chemistry. A nucleus consists of protons and neutrons, and these protons and neutrons are held together by the strong nuclear force. That strong nuclear force is 100 times stronger than the electric force, which holds the positive nucleus and the negative electrons together in the atom. Nuclear physics studies how the energy changes when nuclei are combined and when they're taken apart. So let's look. Which are the easiest nuclei to combine or take apart? Iron, with 26 protons, is the hardest to take apart. It has the greatest binding energy. And so fission, when we split nuclei much larger than iron can release energy when they're split up. And fusion, combining nuclei much smaller than iron release energy when they're fused together into a bigger nucleus. Hydrogen nuclei, which are the smallest, provide the most energy when they're combined. That's what happens in the sun. The biggest nuclei, like uranium, provide the most energy when they're split or fission. Either way, nuclei provide the most powerful source of energy in the universe through nuclear fission and nuclear fusion. Fission is the energy behind the nuclear bombs that were dropped on Hiroshima and Nagasaki, the hundreds of nuclear power plants worldwide providing electrical power, and the nuclear submarines, nuclear aircraft carriers, and nuclear icebreakers. Energy from fusion is harder for humans to harness. We can do it in hydrogen bombs, which use intense heat from fission bombs to fuse hydrogen into helium, making a thermonuclear weapon. Scientists are working on the dream of fusion-based nuclear power to provide clean, seemingly unlimited power by fusing isotopes of hydrogen into helium. But fusion is where the sun gets its energy for billions of years, from fusing hydrogen to helium and then later helium to carbon and oxygen. All of our energy, from solar power, wind power, hydroelectricity, coal, oil, natural gas, originally comes from hydrogen fusion in the sun. However, nuclear physics is far, far more than just a couple of controversial applications. Nuclear physics is about everything possible that can be done with the nucleus. For me, nuclear physics is much more about studying collisions of nuclei in experimental halls, like at the Thomas Jefferson National Accelerator Facility, where I do my research and where we seek to advance fundamental knowledge. Here in this first lecture, we're going to do a whirlwind tour of nuclear physics. But don't worry, we'll explore all of these topics again, step by step, later in the course. Now, the periodic table is great for organizing atoms. We just count the number of protons, we'll have the same number of electrons if it's a neutral atom, and then, well, hydrogen is basically 1 helium is 2 neon is 10 uranium is 92 But each element, and each element corresponds to a specific number of protons, has more than one possible nucleus. These isotopes, what physicists call nuclides, have a different number of neutrons. So if we look at carbon, carbon has 6 protons. Carbon-12 with 6 protons and 6 neutrons is the most common isotope. It's the most stable one. Carbon-14 still has 6 protons because it's carbon, but with 8 neutrons is famously unstable. But carbon has isotopes ranging from carbon-8 with only 2 neutrons to carbon-23 with 17 neutrons. Chemists are justly proud of the periodic table with more than 100 elements, but nuclear physicists are even more proud of another table organizing over 3,000 isotopes in what's called the table of the nuclides. It shows all of the known nuclei, and more are added all the time. So there's the number of protons on the vertical axis, the number of neutrons on the horizontal axis, and the stable nuclei go in a band from the lower left to the upper right. The stable isotopes are shown in black, and the color on the chart tells us the lifetime of the nucleus. And so the lighter the color, the shorter the lifetime. Some 250 isotopes are stable. They don't decay, they don't change. These inhabit the valley of stability, and 80 of the familiar elements have at least one member, one stable isotope. So for example, hydrogen has 2 stable isotopes, 1 proton and then 1 proton plus 1 neutron. Helium has 2 stable isotopes, helium-3 and helium-4. Oxygen has 3 stable isotopes. Tin has the most, with 10 stable isotopes. And the heaviest element with any stable isotopes is lead with 82 protons. So what would it take to transmute lead with 82 protons to gold, 79 protons? This was the dream of the alchemists. Well, we can't do it with alchemy or with chemistry. What we have to do is we have to put the lead in a particle accelerator and hit it with some high-energy particles. There'll be some nuclear reactions. Some of those nuclear reactions will knock out 3 protons from some of the lead nuclei and convert those lead nuclei to gold. This can be done, but gold's not worth it. We use reactors and accelerators to make much more valuable isotopes. We might make fluorine-18 or technetium-99 for medical purposes. And in fact, 1 gram of molybdenum-99 that is used to make the technetium for medical tests, 1 gram of that is worth tens of millions of dollars. By contrast, a gram of gold is only about $30 or $40. In addition to the stable nuclides, another 80 or more nuclides found on Earth decay naturally, some very slowly. From 1901, Ernest Rutherford and Frederick Soddy began to notice parts of what we now call the thorium decay chain. They found that thorium, element 90, spontaneously decays into radium, element 88. And then radium spontaneously decays to radon, which has element 86 with 86 protons. And it continues. Well, Rutherford had already named the 3 types of decay radiation, even before there was any evidence that elements were being transmuted. And so he called alpha decay. And in alpha decay, a nucleus gives up 2 protons and 2 neutrons. There's beta decay, where a nucleus emits an electron, and one of the neutrons emits that electron, turns into a proton. And there's gamma decay, where the nucleus emits a high-energy photon, a high-energy particle of light. Soddy coined the word isotope, and one piece of trivia is that H.G. Wells dedicated his story about, quote, atomic bombs to Frederick Soddy. That story was where the term atomic bombs came into use. One more fact, the geology of our planet depends on this spontaneous transmutation of elements. Very slow decays of uranium, thorium, and even an isotope of potassium provide heat that keeps the Earth's core molten. The Earth's core being molten means that the Earth remains geologically active and the continents keep drifting. This happens because these isotopes have very long half-lives, comparable to the age of the Earth. The half-life of common uranium, uranium-238, is 4.5 billion years. Half-life is a time for half the element to disappear. The Earth is also about 4.5 billion years old, so about half the uranium-238 has decayed in this time. The half-life of thorium-232 is 14 billion years, so most of the thorium that we started with is still here. Other isotopes decay much more quickly. Carbon-14 is an isotope created in the atmosphere by cosmic rays that decays with a half-life of just under 6,000 years. Now, here's how we write carbon-14 in nuclear physics. We write C for carbon, just like the chemists. Then we write the 14 on the left side of the carbon as a superscript. That's the number of all the nucleons, the protons and the neutrons. That's the atomic weight. And even though carbon always has 6 protons, because it's carbon, we sometimes explicitly show the number of protons. So we write a 6 on the left side as a subscript. And we do this because sometimes it's nice to be reminded, especially for less well-known nuclei. And we usually subtract 6 from 14, so we know we have 8 neutrons, but for completeness, we can also write the number of neutrons, in which case we put that on the right side as a subscript. Isotopes used in nuclear medicine diagnosis for various scans have half-lives that range from a few minutes to several days. After one half-life, half of the original isotope has transmuted into a different isotope. After 10 half-lives, 99.9% of the original isotope has transmuted into a different isotope. This was originally quite shocking. Atoms had been thought the permanent, fundamental building blocks of the universe. When Marie Curie introduced the notion of radioactivity, she was describing properties of a new element that she'd discovered. This was the element thorium. But also, she showed that atoms can decay, and that means that atoms are not the fundamental unit of matter. The 20th century was the first century of nuclear physics, beginning with Röntgen's discovery of X-rays in 1899 and Rutherford's discovery of the nucleus in 1911. Since then, dozens of nuclear physics Nobel Prizes have been awarded in both physics and chemistry. Nuclear physics developed only recently because the nucleus is so much smaller. The nucleus is 10,000 times smaller than the atom. What does that mean? If the nucleus is the size of a tennis ball, about the size of a fist, then the outermost electrons are orbiting 5 football fields away. So individual neutrons and protons, which we call nucleons, are even smaller. They're several times smaller than the nucleus. The size of a proton and neutron is about 10 to the minus 15 meters. That's 1 femtometer, which we call 1 Fermi in honor of a great nuclear physicist. The quarks and gluons are at least 1,000 times smaller than that. Wait a minute, why do we care about quarks and gluons? That sounds like particle physics. Well, what's the difference between nuclear physics and particle physics? Both are subatomic, both use accelerators. Particle physics, also called high-energy physics, studies the particles themselves, the particle zoo, and it looks at the forces among them and the properties of the particles. Nuclear physics studies how the particles combine, how protons and neutrons combine to form the nucleus, and how quarks and gluons combine to form the protons and neutrons. Now, nuclei are small, but they contain 99.9% of the mass of the atom. So we said they're made of protons and neutrons, and the number of protons determines a chemical element. Chemists generally don't care about the number of neutrons. Chemists average the total number of protons plus neutrons for all the isotopes in their sample into something called the atomic weight. For carbon, that atomic weight is 12.01. Protons provide the electric field that keeps the electrons in orbit of the atoms. But the electric field pushes protons apart. What holds the nucleus together? At small scales, we encounter the strong nuclear force. This affects both protons and neutrons equally, and we need both protons and neutrons to make the nucleus stable. And the strong nuclear force is holding it together, the repulsive electric force is trying to push it apart, and the nuclei that result come from the interplay between these two forces. This interplay changes as nuclei get larger. Lighter nuclei have about equal numbers of protons and neutrons, but the heavier nuclei have up to 1.6 times more neutrons in order to make up for the electrical repulsion of all those protons. Now, the stable nuclei, we said, are in this valley of stability. What if we leave the valley of stability? Well, there are two possibilities. There may be too many protons, too much positive charge. The nucleus needs to get rid of protons. How does it do that? It does it by something called beta plus decay. The proton decays to a neutron plus a beta plus. That's actually a positively charged electron called a positron, which is the antiparticle of the electron, and a neutrino. So proton can decay to neutron, positron, and neutrino, or a proton can combine with an electron to become a neutron plus a neutrino. And so we've changed a proton to a neutron. The other possibility is there may be too many neutrons. That means there are not enough protons. And so there's beta minus decay, where the neutron decays to a proton plus an electron plus an antineutrino. Nuclear waste is basically a problem of excess neutrons in the fission products compared with the same number of neutrons in the original uranium or plutonium. As the fission products decay, they change neutrons to protons, and they move up and to the left on the chart of the nuclides towards the valley of stability. The drip lines are the outer limits of stability of nuclei. They're the maximum number of neutrons you can have for a certain atomic number. More neutrons than that, the neutrons drip off. Or the maximum number of protons you could have for the same total number of protons and neutrons. If you have more protons than that, the protons just drip off. What else does nuclear physics consider? Nuclear physics also studies where nuclei come from. The nuclei from hydrogen to helium were made in the Big Bang. Nuclei from helium to iron are made in stars. And heavier elements from iron all the way up were made in supernova and neutron star collisions. This is why scientists like to say that we're all really made of star stuff. There are 3,000 nucleides on the chart of the nucleides, but only a few hundred that we've detected on the Earth. The other 90% of the known nucleides have already vanished from Earth because they decayed away. Their half-lives were too short, and we only know about them because we've been able to create them in a laboratory. So when we make new isotopes, we're making star stuff. And even the most exotic nuclide near a drip line, so would have a very short half-life, may have been part of an unrecognized decay pathway to the formation of elements that do persist. And so nuclides no longer found on Earth may turn out to have been very important to our very existence. How do we study nuclei? Well, we study them like a 5-year-old studying a mechanical alarm clock. We hit it hard and we see what comes out. Well, to hit it hard, we need a very small, which is to say a subatomic, hammer. And we use a variety of large accelerators to accelerate different types of hammers. We can accelerate electrons. We can accelerate protons. We can accelerate other nuclei. And then we take those hammers and we pass them through a target containing the nuclei we want to study or modify, and we use large particle detectors to measure the individual subatomic particles or nuclei that emerge from these collisions. We reconstruct the subatomic collisions using energy and momentum conservation, just like we reconstruct car crashes to find out who was at fault. The difference is collisions between cars damage the cars, sometimes severely. Subatomic collisions can make new nuclides. It can knock nucleons out of a target to make smaller nuclei, or we can combine two nuclei to make larger ones. For example, if we accelerate zinc and we hit lead with zinc just right, we could create bigger nuclei. We could create a nucleus called Copernicum. So we take lead with 82 protons and 126 neutrons, so 208 total nucleons, and hit it with zinc with 30 protons, 70 total nucleons. We could make Copernicum with 112 protons and 277 total nucleons. And that's how we make either the very heavy or the unstable nuclei. Well, we study nuclei because we want to learn how the world works. And in fact, the average American pays $2 per year for basic nuclear physics research. And what we get from that is a combination of basic knowledge and useful application. Understanding nuclear physics lets us develop more applications. We can use external beams, beams of X-rays or protons, or we can use internal radioactive isotopes for medical imaging, using isotopes like technetium-99, or for medical treatment for killing cancers. We can also use it for other purposes. We can use it for industrial, archaeological, and art analysis. We can X-ray samples. We can use neutron activation analysis. We can date it with radioactive isotopes such as carbon-14 and others. Now, let's look at the structure. Atoms are made of electrons orbiting the nucleus. Nuclei are made of nucleons, neutrons and protons, orbiting each other. Nucleons, like electrons, obey a fundamental rule. Two identical particles cannot occupy the same state at the same time. We call this the Pauli exclusion principle. Because of the Pauli exclusion principle, electrons stack up in orbitals. There are S shell orbitals, P shell orbitals, D shell orbitals in atoms. And the Pauli exclusion principle says, no, we can't put all the electrons in the S shell. You can't put more than one particle in the same state. Similarly, protons and neutrons occupy similar S shell, P shell, D shells in nuclei, just in a different order. So just like atoms, nuclei can be in excited states, and then they de-excite by emitting a photon. When an atom de-excites, it goes from an excited state back to its ground state, it gives off light, often visible light. When a nucleus de-excites from an excited state down to a ground state, it gives off a gamma ray, just a higher energy photon. So one of the most important applications of this is technetium-99 that we use in nuclear medicine is actually in an excited state. And it decays to its ground state, giving off a gamma ray, and we use that gamma ray to see what's going on inside the body. Now, while the strong force is the most important, nuclear physics makes use of all four of the fundamental forces of nature. We use gravity, electricity and magnetism, the weak nuclear force, and the strong nuclear force. Now, it may be surprising that gravity is important for nuclei. It's the most important force at large scales, right? It's what attracts us to the Earth. But on smaller scales, we don't even notice it. There is a gravitational attraction between you and the person standing next to you, but it's almost impossible to measure. And so on really small scales, on subatomic scales, it's the weakest force. It's less than a billion times as strong as the electromagnetic force. Now, what gravity does is it affects everything with mass. And it's crucial for neutron stars. Neutron stars are the biggest nuclei there are. They've got about 10% protons, 90% neutrons. The mass is 1 to 2 times the mass of our sun, but the radius is only about 10 kilometers or 6 miles. That would be a very short daily commute. And what neutron stars do is there's something called the neutron degeneracy pressure. They're pushing outwards, and this is because of the Pauli exclusion principle, and gravity is pushing in. And so it's the balance of gravity and this neutron degeneracy pressure that determines the features of neutron stars. The next force is electricity and magnetism. And where it primarily affects us in nuclei is that the protons in the nucleus repel each other. And then, of course, it attracts the electrons to the nucleus to form atoms. And the range of the electromagnetic force is very long, so it extends over the whole nucleus, and so every proton in the nucleus can repel every other proton. And it's the electromagnetic force that's responsible for that gamma radiation that we just talked about. Then there's the weak nuclear force. This affects all particles. Now, you might think that this is a misnomer because the weak nuclear force is stronger than gravity at very short ranges. But we call it the weak nuclear force, not in distinction to gravity, but in distinction to the strong nuclear force. The weak nuclear force is transmitted by particles exchanging these massive particles called the W and Z bosons you may have heard of. Those each have 100 times the mass of the proton. And so it's like instead of pushing your friend away from you, you push your friend away by throwing a medicine ball at him or her. That's exactly how this exchange of massive particles works. But because they're so massive, the weak force has the smallest range of all the forces. And we're saying, well, wait a minute, what does the mass of this exchange particle have to do with the range of the force? Well, it comes in through the Heisenberg uncertainty principle. The Heisenberg uncertainty principle says that the uncertainty in the energy times the uncertainty in the time is going to be about the size of Planck's constant. Well, the uncertainty in the energy comes from the energy we need to create in order to make this massive particle. And the uncertainty in the time is how long that massive particle can exist. So the uncertainty in the energy is really big because the particle is very massive. That means the uncertainty in the time is going to be very small. That means that particle can't travel a long distance. It can only travel a short distance. And so the range of the weak force is 1/500th the radius of a proton. Very, very, very short. This weak force doesn't help hold the nucleus together, but instead it can change protons into neutrons or vice versa through beta decay if the nucleus is on the slopes of the valley of stability. Now, free neutrons are always unstable because they're slightly more massive than protons, and they decay by the weak force into protons. So a neutron, a free neutron, goes to a proton plus an electron and an antineutrino. What about neutrinos? Well, neutrinos are produced by beta decay. They've got no charge and very little mass. They only interact incredibly weakly, but we care about them in nuclear physics because, amazingly enough, it's the pressure of these neutrinos that makes supernova explode. The strong nuclear force, that fourth force, is the most important of the forces for this course. At a fundamental level, the strong force holds the quarks together into protons and neutrons. This same strong force also leaks out of the protons and neutrons to hold the protons and neutrons together into nuclei. This is just like the way that neutral atoms attract each other to form molecules. They do it through the electric force that leaks out. Well, how does an electric force leak out of an atom? Atoms are neutral. The negative electron balances the positive protons. Helium is a closed shell, symmetric. So very little force leaks out because you've got the symmetric sphere of electrons around the proton. And so helium and other noble gases are inert. But if we look at sodium, it looks like there's a symmetric core with one electron orbiting. And so that means that we've got this sort of positive core and negative electron. And so a lot of the electric force can leak out, and sodium is very, very reactive. So the same thing happens with protons and neutrons. The three quarks form a proton, and then the force that leaks out of the proton is what attracts it to other protons and other neutrons. So what about these quarks? Well, they've got colors instead of charges. We call them red, green, and blue. And because it's colors, we call this force quantum chromodynamics, chromo for color. The force is carried by particles called gluons, and it's a very strong force. So the neutrons and protons are made of three quarks each, mostly, but only 2% of the mass of the proton or neutron comes from the quark masses. This is the 2% that's explained by the Higgs boson. In nuclear physics, we aim to understand the other 98% of the mass. The full quark structure of the nucleon is very complicated. I said there are 3 quarks, but there are also quark-antiquark pairs and gluons. And in fact, the closer we look, the more quarks and antiquarks we see. Nuclear physics has only started to apply quantum chromodynamics directly to an entire nucleus, instead of just to a proton or neutron, in the second decade of the 21st century. We're just starting to learn how the quark structure of protons and neutrons changes slightly when they're in nuclei instead of by themselves. Now, the force between the protons and the neutrons can be described as being carried by a particle that's 1,000 times lighter than the particles that carry the weak force. And so the fact that it's 1,000 times lighter means that the range of the strong force is 1,000 times longer than the range of the weak force. Why does this matter? Well, to interact, a high-energy particle has to hit its target within the range of the force. And that means that a weakly interacting particle has to hit a circle with a radius 1,000 times smaller, and the area of this circle is 1,000 times 1,000 is 1,000,000 times smaller. This means that the strong force is about 1,000,000 times stronger than the weak force. Atoms change, we now know, in 3 fundamental ways. There's alpha decay, when the strong force can't hold the nucleus together. There's beta decay, which converts protons to neutrons or vice versa via the weak force. And there's gamma decay, which is a release of excess electromagnetic energy. In the next lecture, we'll explore more closely how the interplay of the electromagnetic and strong forces makes the nuclei we know.